Hi, it's time for another math easy solution. Time to discuss a pretty interesting discovery project. Basically, discovery projects are at the end of each chapter in my textbook. They have these pretty interesting math projects, and I want to go over this one because it's pretty interesting. And this one's about rotating on a slant, and it's again based on applications of integrals and finding the surface area. So in this one, we're going to go over question 1 of that discovery project. And basically, let's just go over it. So discovery project, rotating on a slant. We know how to find the volume of a solid of revolution by rotating a region about a horizontal or vertical line, just like I went over in my earlier videos. We also know how to find the surface area of a surface of revolution if we rotate a curve about a horizontal or vertical line. But what if we rotate about a slanted line? Basically, let C be the arc of the curve y equals f of x. That's just C right here. This is just the curve between the points P, so capital P to Q, where this is just P of f of P. Like that, this is just f of P, etc. And this is f of Q over there. And so these are the points P, Q, all the way across to there and there. And let R be the region bounded by C, so that this is the region R, then shaded in gray, by the line y equals mx plus b. So it's just a line, slanted line, which lies entirely below C. So this is, it doesn't cross it in any way. So this is just below it. And by the perpendicular lines P and Q. And these are the perpendicular lines across like that. So it's basically this shape. It's we're looking at it in respect to this slanted line as opposed to this what we normally would do is the x-axis or the y-axis. And now, so the question 1 that I'll cover is basically this one states, show that the area of the region R is equal to 1 plus m squared, where m again is the slope of this line, times the integral from P to Q of f of x minus mx minus b, all times by 1 plus m times the derivative f prime of x dx. And a hint that my calculator gives is basically this. This states this formula can be verified by subtracting areas, but it will be helpful throughout the project to derive it first by approximating the area using rectangles perpendicular to the line, as shown below here. Above. So basically, we're going to sum up using these rectangles about this line. You could solve it again, like I stated here in this hint, by subtracting areas, but basically deriving it by the old-fashioned summing up infinite rectangles to get an integral will be useful throughout this whole project. And also says here, use the figure below to express delta U in terms of delta X. So this is the hint that the textbook gives us. So it gives us this image, and it helps us basically convert this delta U into everything into delta X, which we're gonna have to solve it by. So let's go over the solution. So solution to number 1, to question number 1. So we're asked to find the area of this region, and we're going to find it using just the rectangular infinite rectangle method. So if we have this shape like this, if we just assume we're always dealing with this slanted like this, then basically the area is going to be roughly equal to, this is going to be limit as n approaches infinity of the integral from, this is going to be n equals to, let's go n equals to 1 up to infinity. So I equals to 1. Up to n right here. I got that mixed up. So I equals to 1 up to n, where n is approaching infinity. And then so we take a small section, which is this triangle, and this is delta U, and we'll consider this point here to be Li. So the area of this rectangle is going to be Li times delta U, but then we're going to sum it up to infinity. So it's going to be Li times it by delta U. So this is the area. So we need to find Li and delta U in terms of x. And again, this equals to, when you write it as a limit, I mean, as an integral, this is going to be integral from, yeah, it's going to be integral from, well, if we consider L as a function of u times by du, and then this is going to be from, well, it depends on what this is. We'll call this point u of p. This is uq. So that's when x is q or u is uq. So this is, let's call this uq. This is just for illustration purposes. So we're going to just write everything in terms of x. So the idea is write li, so find li and delta u in terms of x. Yeah, so that's what we are going to try to find. So now to find this, we're going to basically use this this hint right here, and as you can see, this line is tangent to the point xi, f of xi, like that. So that's at, let's say, this random point here. We'll call this xi, and then x, yeah, so we'll just call that f of xi. So this very point all the way down as xi. So this slanted curve like that, I mean this slanted line, well, let's just draw that right here. So at that tangent line across it, at this very point xi, and this curve, I mean this angle we're given is, this is alpha. So that's alpha. So since this is tangent, then the slope of this line is going to be the derivative at this point. So this slope is going to be, let's call this, this slope right here at this point equals to the derivative. So at derivative at this point, that's what the definition of derivative is just the instantaneous slope at any point, and at this point is just going to be the slope at this point. And it's always changing for whatever x is, but at this point, that's the slope equals f of xi, which again, the slope is just equal to rise over run, which is the same as tangent since we have an angle. So I'll put it here, thus tan alpha is this equal to, well, the derivative. Rise over run, yeah, so this is just equal to that, which is just rise over run. Definition of tangent is rise over run, so this is f prime of xi. So that's the first thing we know. We're going to use this in the derivation. Yeah, and now the delta x right here, let's just draw another part here so that the distance across this is going to be delta x, like that. And now if we were to draw, and again this is f of y equals f of x there. Actually, I mean this is the tangent at that point, not y equals f of x. So now if we draw the slanted line, something like this, this has an angle beta, and now we're gonna transpose this across in a perpendicular line here. These are perpendicular lines because everything's dealing with about this. So it's perpendicular, so 90 degrees on both sides, and this is our delta u from there to there. Yeah, and we need to find this li. So, and now one interesting trick to solve this, well, we got to find li and delta u. So let's look at delta u. If we draw a parallel line to this one across at this very point, so let's draw this exactly the same parallel line. Ask and draw it all the way down. Let's draw that a bit straighter. Oh, it's not lining up with it. Let's just do this way, like that. Okay, I think this is, so this is just it's not drawn perfectly, but assume this is perpendicular, I mean not perpendicular, parallel to this one. So if it's parallel to this, then basically this angle is beta. And then this angle right here, so again this is going to be, it's parallel, so these are all right angles across this whole thing. So that's all 90 degrees. And then what I'm going to do is I'm going to write an angle like this. I think it's theta, I think that's how you call it. I'm not sure what this one is. So we have that. We can determine what this is because at this point is just 180 degrees total. So this angle about this is just 180 minus beta. And I'll show you why we're going to solve that. So basically, because now this is a triangle, so the total angle in a triangle is 180 degrees, and you could prove that. I proved that in my earlier video. And I'll write that here. Recall sum of angles in a triangle is 180 degrees. So in this case, we have then these three angles, alpha plus, I think it's theta, let's call that. So, and then plus this 180 minus beta. This has to equal 180. So there's 180 positive on both sides. We can just cancel these, and then we could shift everything to the like shift this, and keep this here, shift this to the right, shift beta to the right. We get this theta is equal to beta minus alpha. So we have this angle, and the reason we're doing that is because if we look at here, if we look at this point right here, we have this length here, which is going to be our delta U. That's just this shifted here. And this is a right angle triangle across here. So if we can solve what this d, we'll call this di, if we could solve this distance, and we can solve for delta U. So we know, if I were just to draw this triangle on its own, so we have this, something that looks like this, where, actually this is the other way around. This is a right angle. Let me draw this a bit better. So this is a right angle, this is alpha, this is delta U, and then this is di. So if we could solve for di, we can solve for delta U. So first let's just write in terms of di. So the cosine of this theta is just equal to adjacent over hypotenuse. Adjacent is di over this delta U. So our delta U is equal to di times it by cosine theta, like that. And now, so we could solve for this di by, well, look at this delta x across here and just shift this up above here. So we can write it like, let's say this, I'll write it softly. So we have a triangle like this, where this angle is alpha, and then this distance across, this is just delta x, and we have a right angle triangle. And I'll draw that out separately here in gray. So we could have something like this, where this is our di, this is a right angle triangle, and this is our delta x, and then this is our alpha. So here we get, well, the cosine of this now, cosine alpha is equal to delta x over di, adjacent over hypotenuse. So the di is equal to, shift this around, delta x over cosine alpha. So we have this, I'll write this like that, di. Now we can just plug this inside. So we have delta U is finally equal to, this is going to be delta x times it by, and this is cosine alpha. And this one right here is cosine theta, where cosine theta, well, theta is just equal to this. So this equals 2, write this out, delta x, this is going to be times cosine beta minus alpha divided by cosine alpha. And now we can simplify this cosine beta minus alpha by using the trig identity. Well, let's just recall, which I covered in my earlier video. Recall the trig identity, and you can see that in the video links below. I put a link there. So recall the trig identity. Cosine of this of this x plus y is x plus or minus y, and this is going to change the signs. It's going to be equal to cosine x cosine y minus or plus. So if it's plus, we minus. If it's minus, we plus. And then we have this sine x sine y. So in this case, we have a minus right here. So we minus. So since we minus, we plus. So let's plug that inside. So we have delta U is equal to delta x times it by, let's just divide this right here, cosine alpha, and then we have times it by cosine, this is x, which is going to be beta, and then cosine alpha plus sine, this regular bracket, I'll put this bigger, so plus sine of beta sine of alpha. So that's what we have now. We could divide this, we could cancel this out, and then what we end up getting is equal to delta U is equal to, I'll just write equals to instead, delta x divided out, we get cosine beta plus, here we get sine beta times sine alpha cosine alpha. This is just tangent. So we finally get delta U is equal to delta x times it by cosine beta plus sine beta times it by tan alpha. And now, this is going to be useful that we already solved our rise over run. Tan alpha is equal to, well, this derivative f prime of xi. So this just equals to delta x, this cosine b plus sine beta, this is going to be f prime delta xi. Put it like that. But now we could also solve for these cosine betas as well, because we scroll all the way back up here. This curve is just y equals mx plus b, where this is the slope. So we know that, and then this is the beta. So what we know is slope equals m of the slanted line, which again equals to rise over run, which just equals to, in our case, this is just going to be tan of beta. So tan of beta, you could also write this as, well, m over 1, rise over run. Just draw a triangle like this, where this is rise 1, this is when over the slope is 1, and now this, using Pythagoras theorem, this is just the side squared plus this guy, side squared, so we have 1 squared plus m squared, all square root, and this is our angle beta. So we know that yes, we have tangent. Now we can just solve for cosine. So cosine beta is equal to adjacent over hypotenuse, 1 over 1 plus m squared, all square root, and then sine beta is just going to be equal to opposite over hypotenuse, so m over 1 plus m squared. So now we could just plug these inside, and we get, basically we get delta U is equal to, again, delta x cosine b plus sine b times it by f prime of xi. Now plug these inside, we get delta x, then we have, this is 1 over 1 plus m squared plus m over 1 plus m squared f prime of xi. Let's simplify this further by taking this common denominator out. So we get equals to delta x 1 plus m squared, all square root. This is 1 plus m of x, f prime of xi. This is our delta u now. So we've solved delta u, and we've wrote it in the terms we know, which is the m, we have the delta x, and this xi. So we're not using the u variable. And now what we're going to do is, well, we need to solve for the Li. Let's just go back up here. So we need to solve for this Li, and I'll show you a trick. So this is, we'll call this Li again, this is our Di. What I'm going to do is extend this line all the way down. So this is a pretty interesting trick in solving this one. So for Li, let's draw that same tangent line, like that. And then at this point we have, let's just go bring this all the way down. So what I'm going to do is we have this part, where again this angle right here is just alpha, and then I'm gonna extend the slanted line all the way until we cross this straight line. So I'm just gonna extend it like that, so that we have this is our xi, and then what we have at this very point is, well, this angle here is beta of this, and then this we know is y equals mx plus b, and at this very point this is just our f of x I, because again this is the tangent line, yeah, at xi, f of xi. So at this very point it's tangent like that. So the reason we're going to have this, because we're going to need to solve for our li, which is, again, draw this perpendicular to this. This is our li. So the fact that we've extended it all the way down here is because, well, since this is y equals f mx plus b, this total distance across here, this is just, well, f of xi, which is the full length. So this is f of xi, and then this distance from this point on this slanted line is just going to be, well, it's y equals mx plus b, so plug in xi, so this is just mxi plus b. So here, so this line segment across is just f of xi minus mxi plus b. So it's just subtraction of the two. And the reason we're doing that is because now we have a right angled triangle with a hypotenuse side here that we know, which is f of xi minus mxi plus b. Let's write this neater. Yeah, plus b. So we know this whole section, and now we can find this angle. This angle right now, this is 90 degrees. That's just a line like that. So this is 90 minus beta. So then 90 minus beta, and then this angle right here, we can solve it because, well, let's just call this angle capital A. So again, it's a triangle, so that A plus, this is 90 degrees. 90 degrees, I'll just erase the degrees. So 90 degrees plus this 90 minus B has to equal to, well, 180. So this is 180 right here. So the 80s cancel. We're left with A minus B equals to 0. So A equals to beta. So this equals to beta. So we could use the cosine of this. So what we end up having is a triangle that looks like this, a right angle triangle that goes down like that, where this angle is beta, this is our li, and this part right here is f of xi minus mxi plus b. So since we have this is just using cosine now. Cosine of beta is equal to li times divided by the hypotenuse, addition of our hypotenuse, f of xi minus m of xi. I'll just subtract it out, so negative mxi minus b, like that. So we have this, thus, and then we're cosine b again. We already solved this. Let's just go all the way back here. So the cosine b is, we've solved this before, or beta 1 divided by 1 plus m squared, all square root. So this equals to, I'll just put this down here, which again equals to 1 over 1 plus m squared. That's this cosine b. So solving for it, we get li is equal to, well, again, cosine beta times it by f of xi minus mxi minus b. And then this cosine, that's just going to be, let's write it like this, f of xi minus m of xi minus b, all divided by 1 plus m squared. So we have our li and we have our delta u. So now that we have these, let's just go back to that area formula we had written. Area is roughly equal to limit as n approaches infinity Actually, it's not roughly. This is equal to it by definition of the area. It's as it goes to infinity, equals 2, and then you have delta. And then we have a limit n goes to infinity of I equals 1 up to n. So this is just saying we have infinite number of these rectangles. So we just keep going on and on and on, like I've went over in my earlier videos on integration and area. So I'm not going to go over in too much detail why that's so here. So then by definition this equals to the integral here. So we just plug in the Li and delta U. So we get right here, let's go all the way back here, so thus area is equal to the limit as n approaches infinity of, this is up to n, I equals to 1, of Li times by delta U, where this equals 2. Let's write it down. Actually, let's write it here. So equals to limit infinity I equals 1 of, now we have Li, which is that. This is f of xi minus mxi minus b. That's 1 plus m squared. And then we multiply this by delta u, which was, let's just scroll back up. So delta u is this, delta x times, divided by 1 plus m squared, and then times 1 plus m f of x I. So this equals 2, like this. This is 1 plus m of f prime of xi over 1 plus m squared, and then we have the delta f, let's take it out. So we have it this, like this is the Riemann sum, this is the definition of an integral, and since all these are in terms of x, this is equal to, and also we could multiply these 1 plus m squared and move it out of the summation or the integral. So, and then these cancel out, the square root cancels, 1 plus m squared times 1 plus m squared when it's both square root, they cancel, so we're left with 1 plus m squared. And then this is the integral since we're dealing with terms of x. So in terms of x, right here, this u of p is just, we're just going to be dealing with p instead of u of p. We're just going to be dealing with here to here since everything is in terms of x. So we plug that in. So this is p, q, and then here we've taken that out. So we have this f xi minus mxi minus b times it by 1 plus m f prime of xi. Actually, no, there's not xi anymore. The summation, this is any number, and that's any point. This is just because when you're dealing with infinitely small intervals, this is just x. So yes, so my mistake there. And then this delta x becomes dx for infinitely small. So this xi is infinitely small. I mean the delta xi is infinitely small, so that this is any point x, as per the definition of integral. So we have this. And now, let's just circle this, and this is the exact answer we were trying to derive. So f of x minus mx minus b times 1 plus m times f prime of x dx. Let's just go back up to double check the answer. So 1 plus m squared, integral from pq, f of x minus mx minus b, 1 plus f prime of x. So this is the exact same as the one we got. And basically, yeah, that's all for today. This is just question 1. Later videos, I'm going to go over question 2s up to 6, I believe. There's 6, and I'll show how you can solve volumes and area and surface area, etc. This one is just to show how to get the area of the region. So anyways, thanks for watching. It's a pretty extensive video, but it's pretty interesting how you could just shift this around using trigonometry, etc. Anyways, all for today. Like always, you could download these exact notes in the link below. And thanks for watching. And stay tuned for another Math Easy solution.